Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem, find kth smallest pair distance. This is a pretty good one. So the idea is, let's go through the first example. We're given an array that might look like this. So if we go through all possible pairs of this array, we would get this element with this guy and this guy. So that's two pairs. I'll draw them like this, 1, 3, 1, 1. And then here we would get all the pairs with it, and it's just 3, 1. And then, at the last element, there aren't any pairs left. So this can be achieved pretty simply with some nested for loops. So you get all the pairs. Now, the distance of every pair is just the absolute difference between both elements. So this one is going to be +2, this one's going to be 0, and then this one's going to be +2 as well. So now if we were to take all of these, put them in sorted order, it would look something like this, 0, 2, 2. And we're also now given a parameter. In this example, it's k equals 1. We want the kth smallest distance among all of the pairs. These are the distances among all of the pairs. So this is the first smallest, this is the second smallest, and this is the third smallest because they're in sorted order. So if k equals 1, we just take the first one. It's going to be 0. In this case, that's the correct output. So it's literally as easy as this to solve the problem. And you can implement it with sorting like this. So obviously the time complexity of this approach is going to be n squared to get all the pairs, then sort this guy. That's going to be plus n log n. And space complexity, I guess you could say it's going to be big O of n. Well, actually, if we're getting all the pairs, it's probably n squared. So this is the most brute force approach. You could technically optimize it by using counting sort or bucket sort on this part. So we wouldn't necessarily need to use the built-in sort, but we would still need the nested for loops to generate all the pairs. So imagine you get all the pairs, but you have an array, which is going to tell you the count of every single difference. So you have 0, you have 1, you have 2, and you have 3 here. So how many differences are of 0? Well, 1. How many differences are of 1? That's 0. How many have a difference of 2? That's 2 of them. How many have a difference of 3? There are 0 of them. So you could get an array like this. Now, the maximum possible length of this array is going to be whatever the max element happens to be in the input, because everything in this input array is guaranteed to be, I think, greater than or equal to 0, or maybe greater than or equal to 1. Either way, it's going to be positive, so we're never going to have any difference that will ever exceed this. Plus, we're dealing with absolute values anyway, so you can ensure that all of the differences will fit an array like this. Now, basically, we changed the problem slightly. So now we still need to generate all the pairs. That's n squared. We don't need to do built-in sorting. So this is the final time complexity, though that's not really an improvement if you were paying attention. This is still the bottleneck. In terms of space, it's not going to be n squared. I guess it could be better or worse than that. It'll be whatever the max element in nums happens to be. That might be bigger than n squared. I'm not sure. You'd have to look at the constraints of the problem. But either way, I'm pretty sure this is time limit exceeded with Python. So this is not the solution we're going to be doing. But we are going to be doing a solution similar to what I showed you a second ago. Just to summarize, the first thing we did was get the pairs, the differences. And then the second thing we did was accumulated all of them in sorted order. So you get something like this. Now, how can we possibly do better than n squared? Well, the only way would be by not generating all of the pairs. How can we possibly avoid that though? Well, we can try to search this array for that optimal value. So let's just kind of remind ourselves that in this example, k is equal to 1, but I think I'll use a different example to illustrate this better. I'll do that in just a minute. But keep in mind that k is always going to be valid. So if we were to generate an array like this, the kth element would exist. This array will be long enough for that. Now, we know that the search space, the solution must be between 0 and the max element in the input. Let's just call that, the max, whatever, for short. So the solution is in this range. And I did actually take a look at the constraints just now. The max length of the array is going to be 10 to the power of 4. So like in our previous solution, we had n squared. So this is the number that n would be. Now, the max element is going to be up to 10 to the power of 6. So this will be important in just a second, but this is the search space, remember. So we know that this search space represents the difference or the distance, whatever word you want to use. And the kth smallest difference is going to be somewhere in this range. We just don't know what it happens to be. Another brute force approach, rather than doing that sort of nested for loop generating the entire sequence, would be to run a binary search on that search space. We want to find the difference such that the difference, like whatever it happens to be, suppose it was 2. We want to find it such that everything from that element and to the left of it, there are going to be k of them. In this case, obviously it's just 0 because at that point, this portion of the array has 1 element. But imagine if k was actually equal to 2, for example. So if k is 2, we want the second smallest difference. In this case, that's this. So first, let me just claim to you that if there is a binary search solution that we can implement, would it actually be an improvement? Well, let's just quickly do a little bit of math. If this is n squared is going to be 10 to the power of 8. If we can do a binary search solution, I'm just going to kind of tell you that the time complexity of it would be doing a binary search on this search space. And that would mean we're going to take the log of the max. It's actually not going to be that simple. I'm just kind of showing you that this is an improvement, and I'll explain like the overall time complexity in a minute. But the other term, for us to validate every like value in this range, it's not going to be a constant thing like usually it is with binary search. For us to check if a difference is good enough, that's actually going to be an n time operation. We are going to have to potentially go through the entire input. So is this an improvement? Well, if we do some math, we get this is going to be 10 to the power of 4 log base 2 of 10 to the power of 6. That's going to be actually pretty small. I don't think it's going to be much larger than like 20 or something like that, because basically this is asking 2 to what power is equal to 10 to the power of 6. The power is what we care about. And keep in mind, 2 to the power of 32 is like a billion. So let's just put 32 in here, for example. Let's take 10 to the power of 4, multiply by 30, just to keep the math simple. Well, this is going to end up being something like 3 times 10 to the 5. So clearly with binary search, this is going to be much improved over the n squared solution. Like n log n is always way better than n squared. It's not even close, especially for big numbers. But okay, so that's why this is definitely going to be an improvement. Now let me explain the intuition of this solution and why it works. So now let's go back to our search space. We know that the solution lies within this range. So if we run binary search, this is like our left bound initially, this is our right bound. We're going to be calculating the middle and checking if that's the solution. Now, conceptually, think about it for a second. We have the middle, and remember that represents the difference or the distance, whatever word you want to use. We want to know, is this difference the one that is the kth smallest in this array? And by the way, this array will not exist. So how do we answer that question? What are we even trying to answer? Well, in terms of this array, if k was 1, remember, we're asking, well, this subarray, right? This is the array with the one smallest element. If k was 2, we would say this array, because this is the element, right? This array is of size k, it's of size 2, and we want the last element from that array. So instead of generating this array, suppose we try to do some counting. We write a helper method that we will use within our binary search to count how many pairs have a difference that is less than or equal to k. Because remember, that tells us like everything to the left, because we want everything that's less than or equal to that difference, because then that's the kth one. Now, the problem with that approach is, let me just summarize it. We want to count where the difference is less than or equal to the middle value that we calculate, which is the difference. So the fact that I'm reusing this word might be confusing, but like that's the candidate, and that's what we're testing. Count the number where the difference is less than or equal to that. The problem with that approach is, imagine the middle value that we have is 2. We're going to count all that are less than or equal to 2. Right now, everything is. This subarray is of size 3. That's because we have duplicates. So in that case, we will say that how many did we count that are less than or equal to 2? Well, we counted 3 of them. If that value, if the count was exactly equal to k, we would have found our result. It was not though, so we didn't necessarily know our result. So since right now the count is too big, we are actually not sure what to do. Should you take the right pointer and set it to mid -1? If you do that, you're actually eliminating the result because this candidate, this middle candidate equals 2, that was the correct solution when k equals 2 at least. So if you set right equal to mid -1, you're not going to get the right solution. So the approach that we're going to take is this. If the count is greater than or equal to k, it could include the solution. Like this subarray that we looked at could include the solution. So in that case, we're going to set our right pointer equal to mid. But if the count was too small, suppose the candidate that we tried was mid equals 0, we would have counted this subarray. This is the subarray that includes all elements where the difference is less than or equal to 0. And it's of size 1. Right now, 1 is smaller than k, so we know for sure this subarray is not going to include the element that we want to return. So in that case, we would take our left pointer and set it to mid +1. So right now, I'm just kind of going over the basics of this binary search. Now let me actually show you how we're going to do this counting without generating this array. Okay, so now let's get into this example. And I just want to quickly remind you that if you feel like this, what I'm explaining is difficult, it is possible that, maybe I'm just not explaining it well enough. But I want to say that this is genuinely difficult. This is a hard problem for a reason. Nothing's like in particular that we do is going to be super complicated, but when you piece it all together, it's hard to make sense of all of this. So let's go through this example and hopefully it'll make more sense. So this is our range of numbers and we're looking for the kth smallest difference. Now keep in mind that k could be bigger than the max element in this input. So if we were to take all of the differences between all of these pairs, I think we'd get something like this. I'll quickly draw it at the bottom. I think we'd get, this would be 1, we'd get a 1, we'd get 3, 4, 5, 6. That's all the differences that start with this one. And then I think we'd get 0 from the 2. And you could keep going. Obviously, it's going to be very big. So this will be roughly n squared divided by 2. So k just has to fall within this range, like at a position within this input. So we want the kth smallest. And in this example, I believe it's actually going to be 2. So you can imagine that we'll have some input, which is going to be, I think it's just going to be 1, 0, and then we're probably going to have a bunch of 1s. And then eventually we're going to have a 2. That's going to be the kth smallest. I'm not exactly sure about all of these, but I can guarantee you that 2 is going to be the 7th smallest difference. So now we know our solution is going to be somewhere between 0 and the max element. So I'm going to initialize left to 0, right to 7. And by the way, notice that I drew this array in sorted order. That's actually going to be very important. So sorting the input array is going to be one required step, and that's going to be n log n. We compute the mid between here. We get mid is, I believe, we're going to round down. So I think it's going to be 3 in this case. So that's the distance. Like that's the difference that we're trying. We want to know how many pairs have a difference that is less than or equal to 3. Let's count that. Now you tell me, given a sorted array of the input values, how could you count the ones that have a difference less than or equal to 3? Do you really need nested loops to do that? The answer is no. We can use 2 pointers. More specifically, we can use the sliding window technique. Let me show you that. So we're going to initialize our pointer here. And obviously this isn't a pair. So eventually our right pointer is going to be here. Our left pointer is going to be here. So now within this window, we want to know how many pairs have a difference less than or equal to 3. And more specifically, we're actually going to ask how many pairs ending at this element, because that's something we can actually calculate. So right now it's 1. There's 1 pair. If you take the difference between the left element and the right element, the difference is going to be 1. 1 is less than or equal to a difference of 3. Next, we're going to shift the pointer over here. Once again, the difference is less than or equal to 3. So now we're going to ask how many pairs ending at this element. With the introduction of this element, how many new pairs do we have? Well, to get that, we just take the length of the window. Well, or rather like the difference between the pointers, because that means we have one pair here and one pair there. With the introduction of this element, we have 2 new pairs. So far we've counted 3. Now the right pointer is going to be over here and the left pointer is over there. Once again, we can take the difference between the max and the min element. Right now it's 3. That's a difference less than or equal to 3. So how many new pairs with the introduction of this element? That's going to be 1, 2, 3. So far we've counted 6 pairs. Obviously, if we were drawing out all of those pairs, it would be quite like a long list. We'd have 6 different pairs already. So now our right pointer is going to be here. Our left pointer is still there. Right now, though, we take the difference between these elements. It's going to be positive 4. So we can't say right now that we can create 1, 2, 3, 4 pairs with the introduction of this element, because not all of them are going to have a difference that's less than or equal to 3. Specifically, this last left value over here. So now we have to shrink our window. We got to do the sliding window. We got to increment the left pointer until the difference between these two is less than or equal to 3. In this case, we only have to increment it once for that to be true. So right now, the difference between these two is less than or equal to 3. So now, once again, we take right minus left. We get 1, 2, 3 new pairs with the introduction of this element. So far I've counted 9 pairs with a difference less than or equal to 3. We're going to keep going quickly. So now our right pointer is going to be here. We're going to have to shift our left pointer this time, not just once, but twice. So it's going to be all the way here. With the introduction of this element, we can do 1, 2 pairs. So I think we're at 11. And lastly, we get over here. Left pointer can stay there. We get 1, 2, 3. So I think that's roughly 14 pairs we counted with a difference less than or equal to 3. So now you tell me, is 3 the correct answer? Is the kth smallest difference equal to 3? Well, no, because with 3, we have 14 differences that are less than or equal to 3. I mean, it is technically possible that 3 could be the answer. Actually, it is technically possible. That would be the case where maybe we start with a 0 and a bunch of 1s. At some point, we just get like a long string of 3s. So it's hard to draw all this out because these numbers are big, but imagine that we have an array of length 14. The 14th element, we guaranteed that the 14th smallest element is indeed 3. But we don't know anything about the differences that are to the left of that. So we have to continue our binary search now. But we can't say that our right pointer should be smaller than 3 because, like I said, 3 could be the correct answer. So we're going to set our right pointer equal to 3 because just in case this is the solution, we want it to be equal to that. We want it to still be a part of our search space. So now let's update the binary search and set right equal to 3. Now we're going to continue. We're going to do 0 plus 3 divided by 2. I believe rounding down, that's going to give us a 1. So now we'll get to see the other case. So mid is equal to 1. We're asking how many differences are less than or equal to 1. We're going to do our sliding window once again. So starting left pointer here, and then right is going to start there, but we don't really care about that. Then it's going to be here. Take the difference. The difference is less than or equal to 1. So how many pairs here? Well, it's just 1. You take the difference between the pointers. So far we counted 1. Now right pointer is going to be here. The difference between these is still less than or equal to 1. So we now have 1, 2 new pairs. So far we counted 3 pairs. Now get the right pointer over here, left here. Okay, well, the difference between these two is no longer less than or equal to 1. So start shifting our left pointer. We're going to have to shift it all the way until we reach the 4th element. So with just this element, how many pairs do we have? It's 0, right? You take the difference between the pointers, it's 0. So far we counted 3 pairs. Now let's move the right pointer here and left is still here. Well, this is a valid pair. The difference between these is less than or equal to 1. So this is a valid pair. We counted 4 valid pairs. We're going to get the right pointer here, left here. We're going to need to shift the left pointer. I'm going to kind of go quickly right now. So here we got another valid pair. That's 5. And then eventually we're going to get here and here. That's going to be the 6th valid pair. So we counted 6 differences, 6 pairs, I guess would be a better way to phrase it, where the difference is less than or equal to 1. Now you tell me, does that mean the kth smallest difference is 1? No, it can't possibly be 1. We completely rule that out because there's only 6 pairs with a difference less than or equal to 1. So it can't possibly be the solution. So we will now look for larger differences, because as we increase the difference, we will get additional pairs. So we're going to say our left pointer now is going to be mid plus 1. Now it's going to be 2. So I'm going to strike that out, and now left is going to be 2. So now I'm just going to scribble this out. Sorry. Now, once again, binary search, adding these two, dividing by 2, I think we're going to round down. So mid is going to be 2. How many pairs have a difference less than or equal to 2? I'll go through the sliding window portion pretty quickly at this point. I think left is going to be here, right is going to be here. That's 1. That's plus 2. So we have 3 total. We're over here. So we got to shift our left pointer. We're going to be here. So that's going to be 2 more. So we're at 5 total. Then we're going to get here and here. That's 6 total. This is 7 total. This one is going to be 8 total, I believe. So we counted 8 pairs with a difference less than or equal to 2. So at first you might say, well, we don't necessarily know that the 7th pair is going to be a difference of 2. Yes, but we technically did rule out 3 because we weren't sure that if 3 gave us however many pairs, I think it was 14 pairs or something like that, we weren't sure that, okay, if we take a 2, how many pairs is 2 going to give us? It could have given us less than 14 and it could have given us less than 7. So now what we're going to say is M could be a part of the solution set. It has 8 pairs, so this is technically still part of the solution. So we don't want to remove 2 from our search range. So what we're going to do is set our right pointer equal to middle. It's going to be set to 2 now. And now you notice that our left and right pointers have converged. They're the same. So this is the final solution. This is the smallest difference that will contain the 7th smallest difference. Because if you recall, with a difference of 1, we had 6 pairs. With a difference of 2, we had 8 pairs. With a difference of 3, we had 14 pairs. So 1 did not include the solution. With a difference of 3, we did include the solution, but it wasn't the most precise one. This is the one. The 7th smallest difference is going to be 2. I know this is very, very confusing. It's very, very abstract. It probably would have been easier to understand if you kind of had the entire list of pairs with this array, but that would have been very, very long. It would have been like 20 plus elements and we would have ran out of space. And then I wouldn't have been able to kind of show you the sliding window. I think the hard part about this problem is we're doing multiple things at once. We're doing the mathematics of the differences of all the pairs. We're doing the binary search, and we're doing the sliding window all at the same time. So please don't feel bad if you're not fully able to understand this just yet. But I hope you do believe me when I say the time complexity from sorting is n log n, and then the binary search, given that the log is going to be the max element, let's call that the max, and we're going to do it with a sliding window every single time, so we're going to multiply that by n, so this is the overall time complexity. So now let's code it up. So first, let's make sure to sort the input array. So that's the first thing I'm going to do. Then I'm going to initialize the binary search. Our left and right pointers are going to be 0, and the max element in the input array. Like the differences among the pairs have to be within this range. That's why we initialize it that way. Now we're going to do the binary search, and it's going to be a little bit different than I usually do it for reasons we kind of talked about earlier. I'm going to say while the left pointer is less than the right pointer, we're going to compute the midway point. You could do it like this, left plus right divided by 2. The technically more correct way to do it is like this, left plus right minus left, and then divide all that by 2. And this will just prevent overflows. This is a very minor point though. Now we want to count the pairs with this difference, this middle value. How many pairs have a difference less than or equal to that? So I'm going to use a helper function for that. And then we're going to do what I said. If the number of pairs is greater than or equal to k, this could include the solution. Middle could be a part of the solution. So we're not going to set right to mid minus 1. We're going to set it to mid. Else, that means the number of pairs was less than k. So that means this can't possibly be the solution. So we set left equal to mid plus 1. At the end, the pointers will have converged. And in that case, you can either return left or right, so it doesn't really matter. Now, lastly, for the helper function, just be very clear about what this function is doing. It's going to accept a distance or a difference, whatever you want to call it. And what it's going to do is count the total number of pairs with a difference less than or equal to the parameter distance. And it's not super complicated to do this. This is just a basic sliding window. We're going to have our left pointer. It's going to be 0 initially. Result is going to be the count that we're returning. That's also going to be 0. That's what we're going to return. And then we're going to have the sliding window for right in range, length of nums. To the result, we always want to add the difference of the 2 pointers. That tells us with the introduction of this element how many new pairs were introduced. But we have to make sure that the pairs have a max difference less than or equal to the distance that was given. So we're going to say while the number all the way at the right minus the number all the way at the left. This is exactly why we did the sorting, because this will tell us the minimum element and this will tell us the maximum element within our window. And if this difference ever exceeds the distance, that's when we want to shift the left pointer. So we just increment that by 1, just as easy as that. So this is the entire code, but that does not mean it's simple. I think it's about 20 lines if I got rid of the comments and stuff. But again, that doesn't mean it's easy. Let me just run it. On the left, you can see it works and it's pretty efficient. If this was at least a little bit helpful, you might like some of the resources I have over on Leetcode.io. Thanks for watching, and I'll see you soon.